in. But the beginning of this is quite slow, so it'll probably take 5-10 minutes before we actually start writing some code. Um, so the whole point of this is purely to kind of introduce you to concepts if you haven't seen them before, but the main idea is to kind of just make sure everyone's on the same basis, right? So when we start talking about some of the stuff in the later parts of this course, you don't go, wait, I don't know what that is. And so there's a few parts of this that we're going to be talking about. There's some stuff here like const, which you probably have never seen before. We'll mention const briefly, but stuff like that is not so relevant for the course. So we're probably just going to kind of, you could mostly ignore this. You could probably just not even add this to your code, and stuff like that. So we're just going to try to keep it somewhat focused, but also we'll just kind of keep it a bit wide in terms of what we go through. So the topics we'll be covering will be memory representation. So this is something that I think 1511 does kind of poorly. It used to do it really well, but then they kind of ran out of time with the down to 10 weeks. And so we're going to really cover it, get a good understanding of what the difference is between memory, like how is it laid out, how does it actually work in the operating system, and just kind of have some intuition around it. We're going to be doing a ridiculous amount of pointer work, so much so that almost all the code I'll write will use pointers rather than indexes. This is not for any star reason. It's purely just so that we can see them, right? I've written some code. It's not that much. Probably, I don't have Tokai on this, do I? This is a new computer. I haven't installed everything yet. There's probably only maybe 400 lines maximum. Actually, you know what? There's a lot of like specification stuff like this, which is 50. There's probably like maybe 500, 600 lines. I had to do that basically, otherwise we would have run out of time because I would have spent so long copying this color table. So we can have colors. I would have taken forever to do things like flags and stuff and set all that up. Like all this stuff takes a while. So I'll go through the code, just kind of briefly show you what we've got and what we're going to do. And then we'll talk about some concepts and we'll kind of walk through. So the whole idea of this is at the end we'll have an application that we can use and that will hopefully work mostly. We'll at least have something that can print out a CSV and that we'll be able to edit and move around in the CSV, but maybe we'll be able to add more functionality to it. So the key thing that makes a CSV different than makes most things is that we have basically a very generic data type, right? So as we know in Excel, right, you have like numbers, you have text, you have dates, you have a bunch of various different types. And typically, you know, if you're coming from a language like Java or you're coming from a language like Python, right, you kind of have the same kind of idea, right? So in Java, for example, you'd have a string like this. In Python, you'd probably just do this, right? You'd just say, okay, this is my string, right? And these are extremely different than in something like C, right? In C, you don't have like a string class because classes don't exist, right? So instead, what we have is we have this idea of a struct, right? As most of you know, and struct just like lays out memory. Structs don't actually exist. That's the first thing we really have to be careful of is the structs don't exist, right? They're purely compiler based, right? So in the runtime of your code, they no longer exist and they're just memory. So for example, with this struct here, when this gets compiled, the compiler goes, okay, every time you're talking about a record, I know that it's actually behind the scenes going to just look like a chunk of memory. I'll do one line. And the first, 8 bytes will be the number or text. Then the next 4 bytes, I guess, will be the type. And then the next 4 bytes will also be the column, right? I'll say this is 4 bytes. It's probably just going to be a single byte, but they'll have to be padding anyway, so it will most likely become 4 bytes. And so it's going to lay that out in memory. So every time you ask for a record, all it does is goes, okay, how much space do I need? Well, I'm going to need 8 plus 4 plus 4. So I'm going to need 16. So I'm going to go and allocate 16 bytes wherever you want. So if you want on the heap, we'll go and allocate on the heap. That's like using malloc, right? So malloc is like new in those kind of languages, right? You're just saying, okay, I want something and I want it, and I don't really want to like inside this function. I don't really know when this thing's going to end. It doesn't have a lifetime, right? That's the way I like to think of it, is lifetimes and ownership, right? So something that is stack allocated, which is allocated within a function. So we have some kind of void function foo. case people have questions. And I create an integer here. The time of this integer is within this function, right? And so in C, you can actually specifically state that. In saying that though, what is it? It's auto. That's it. So auto it's actually a keyword in C++, which some of you may know. But in C, it actually means automatically define this lifetime, right? So automatically define this lifetime such that reach this end brace here, it will remove the end. It's implicit, so we don't have to add it. But that really is what the terminology means. And the reason why is because sometimes there's things like register and stuff, which was in the old languages, old versions of C, was slightly more relevant. It was like, hey, I want this thing to be in a register, right? It didn't necessarily mean it had to be in a register, but it meant it had to follow register semantics in terms of how you interacted with it. And then we have things such as, for example, heap allocated memory. The first thing about heap allocated memory that's different from Python and Java and other languages, right, is that you have to specifically ask the operating system for the memory, right? So this is like your new core, or I guess in Python you still have new, right? You can still have constructors and stuff. And you're asking, going, hey, I want this amount of memory. The first mistake people make is they think this is special. This isn't special. This is just for. You're writing C code, right? There's nothing particularly special about what you're writing. You're just saying, okay, I want 4 bytes. That's it. Once you give me 4 bytes, I can walk away and I'm happy. I don't need anything else but those 4 bytes. So what this will do is it will give you 4 bytes and give you a pointer to the first byte. So in memory, it's going to be like OX, blah, blah, who cares, whatever this is, right? And then you're going to have another address, which is going to be like +1, right? Another address, which is +2, and another address is +6, right? So this is your memory chunk for X, right? Your 4 bytes. In reality, this isn't going to be 4 bytes, right? Because we've got to add 8 each time. It depends on whether or not your thing is bit addressed or byte addressed. And in reality, all of our memory addresses are always byte addressed, so it can just be addressed like this. And we're going to have our first address here, and this is going to be X. And X is going to point to this first byte. What this means is that we can do whatever we want to this address. This is just an address, right? It's just like a location. It's not actually anything special. So we can do things like X plus 1 means grab this address and increment it by 1, which will move it over here, right? That's the first mistake that people will think about when they go S1. And the reason why is because C doesn't actually do that. C thinks it's smarter than you, and it probably is. And what it will do is it will go, okay, you're doing X plus 1. So really what you want is you want the next X. You don't want the next address in the current chunk of memory. You want the next version of X. So instead, I'm going to increment this by 4. Because your X is 4 bytes. And so if this is your first X, this must be your second X, with the same kind of thing, whether this is 87 and so on, right? So this should be 87, this should be 8. And so when you increment it by 1, it always increments it by the size of this data type here. So there's 2 ways we can get around that. The first way is that we can use characters, obviously, because they always use the size of 1. The second way is we use void pointers. The void pointer is basically stating it doesn't have an inherent underlying type, right? It's just memory. That's all it's basically saying. And so if you increment a void pointer by 1, it's just going to move the address by 1. You're basically just saying, hey, this is a number. That's all it is, right? This is just a number. I don't really care what the hell you do with it. It's just a number. Go wild, right? And so we care about using that in C in terms of how we do allocations. And so, for example, this array here, and I know some of the stuff seems really simple, but I just want to kind of go simple, then we can go complicated as we build up, right? This array here, or this character array, in memory, you basically will have a series of addresses, 1, 2, 1, 3, 1, 4, and each of these addresses, inside the address, will store another set of addresses, right? And this other set of addresses will be like OX22, OX23, and then this one will maybe store like OX33, OX34, right? And so you kind of get this like double indirection. This almost, let's make this a bit longer just to make. ding. So you kind of get this like table look, right? Where everything kind of has its own section. But these are just numbers. Who cares what the actual value is? They're just offsets, basically. And so the unique thing about a CSV file is that we don't just have strings. Now, typically when we're dealing with CSV in reality and industry, we'll typically just treat them as strings. But when we actually want to do anything with the data itself, we'll figure out what the type is. In this case, I'm just going to convert it midway because we're pretending it's kind of like Excel. So we're stating there's going to be two data types in this program. You can either have numbers or you can have text, right? The first thing that you probably notice about this is that I don't actually have, this is kind of weird. I just have union like this with no name here. I don't have anything here. And this is what we call an anonymous union. What it basically means is you're saying, hey, these two types, yes, they're union, but I don't want to give it like an inner type. I don't want to have this dot inner. So I want to bring these types and bring them outside. So what it will do, the SQL is quite nice here, is it will convert this and pull them outside. So they're basically here. So record dot underscore number, record dot underscore text. Right? However, they're still union. Almost like the union is a hide, it's a facade, right? It doesn't actually exist. We're kind of just going through it, and it's just kind of this like fake layer that we can't actually see when we're coding, right? But it's still a union. It's still going to put the memory addresses right on top of each other. And that's why typically you'll see underscores before them to indicate that this is a union type and to indicate that all of them will share the same memory address, right? As opposed to this here, which isn't a union type, and it's just a normal data member, right? It's just the type of the actual data we're storing, right? And this is called a tagged union. So we're tagging the union that we have that's either number or text with a type, right? So in this case, we're saying it's a number or we're saying it's text. And then we also have the column of the record. So let me show you what a file looks like. This is an example file. We have some animals, we have some ages, and we have some types. So if we have Frankie, who's a fox, we have and my two dogs, right? And I don't know how old Frankie is. Who knows? And so the thing about CSV that makes it unique is it's very easy and very readable, right? So we have commas that separate each of the columns, right? And then we have new lines that separate each of the rows. This makes it quite easy to parse, which is good. So if we look at, for example, how we want to parse this, we basically want to grab every line one at a time, right? And then we want to split up that line based on commas. And now to do that, we're going to have to use string work and we're going to have to use IO work. So that's kind of where I go into the next part, and that's why I'm going to talk about this. But before I go into that, I just want to kind of show a really powerful use of bit flags. So this looks like a huge freaking mess, right? But we can break it down. So we have some configuration types. So here's some configuration that you can define on your CSV file. So for example, you can ask it to skip empty lines or records, right? So you can say, okay, skip every empty line. I don't want to include that as a row. You can also say if it's all empty like this, I don't want to include these because that's quite common, right? Sometimes we have empty records, just ignore them. The next thing we have is, hey, we have some defined headers we want to use instead because maybe your CSV file doesn't have headers. Or maybe you want to override the headers or whatever, right? And then we have the ability to force everything to be a string, right? We have the ability to state whether or not we initialize, and this is a bit different, so you can ignore this for now. Just pretend that doesn't exist for now. But the key thing is there's a few things here. So we have the bit flags, which are defined like this, right? We're stating that each of these occupy a separate bit. So for example, if we map it out, we have a bunch of bits. Now we begin for the right. So the very first bit is occupied by nothing, right? Second bit is occupied by this empty lines here, right? So what this means is that if you want empty lines, the second bit will be toggled. If you want empty records, we'll toggle the second bit and the first bit, right? So that way we have a distinguishment between whether or not you want empty lines or empty records. And the reason why we do it like this is because empty records includes lines. Because if you have an empty line, that's going to be also an empty record. So we make it so that it's basically, if you just toggle empty records, you're also going to implicitly toggle empty lines. The next thing is we have the next bit here, which is defined headers. So defined headers are basically saying, hey, I want to use my own headers, right? So this is going to get its own bit. So this is headers. Then the next bit is all strings. So that's all strings, right? So each of them get their own little bit, and then this is string mode. By allocating everything its own bit, we get a lot of flexibility with our flags, right? So we can toggle them all individually. It's kind of like if each of these was a Boolean. If each of these were a Boolean, right? then we could just turn them all true and false as much as we want, right? But that uses up a lot of space because each of them have to be a Boolean, right? So by using bit flags, we occupy less space and we make it easier in terms of having multiple things at once, right? So instead of just checking one flag, if you want to check if two flags are set, it's kind of the same behavior, right? You would go, okay, if I don't know, flags dot I'm just gonna say b underscore, why not? Just to indicate this is a Boolean. So enum does not need to be sequential. It typically is, and that's called an iota enum. Spelled like this, which is where it begins at 0, goes to 1, then 2, and so on. And you can make it like skipped ones, but they shouldn't be sequential. But you'll notice that this is increasing. We should always make our enums increase just because it's easier to read, but they don't have to be sequential. So we could design like b empty lines, for example. So we're saying if this Boolean is set, or if this Boolean is set, right? So these are my two Booleans, right? And the utility of using flags here is I can grab that behavior that I want and simplify it. And I can basically just say, hey, if flags and this, if this is true at all, doesn't really matter what the value is. If this is non-zero, is what we're basically saying. Then what it means is either it's empty lines or it's empty records. We don't know which one. All we're basically saying is, hey, any of the bits that correspond to this set. That's all we're saying. And we have two bits that correspond to lines and records. Just records, then we could do something like this. Right? Where we'd say, okay, make sure that when we AND it, that all the bits set match the bits that we require for an empty record. So we get this flexibility between saying, oh, are only some of the bits set or are all the bits set, right? And so bit flags are really awesome, but they can be a bit slow because you have to use operations to get them. The next use of a union is, for example, something like this, right? So in this case, our reader can read from a string or can read from a file. It has flexibility for both. This is very common. A very classical case, actually, why not show another code case? A JSON parser, right? That does a similar thing, I'm pretty sure. Why JSON C? I don't know why. I didn't know. I couldn't think of a name for it. Oh wait, it's a single header file. That's why. Okay. This is a big mess. What do I care about my union? You know what? I didn't. I just used normal types here. There must be a reason. Oh, yeah. This is something different though. This is yeah. Okay. This is something special for how we handle buffers in this. There's a very specific reason why we do this. Ignore that. That's something separate. There's a problem with reading. So in this case, what we're going to use is going to fgets to read every line. Yes, only one of the values can be stored within our union. That's the whole point, right? Is that they're optional. It's or. And it doesn't have to be int, float, or string though. Technically, those are going to be like most of the base types, right? But you could have like another one here. You could have like character, have record, right? It doesn't have to be. I mean, it's going to complain because this is not type def to here, right? So it can't see it to there. But if I call it like struct, right? Okay. Let me close my keynotes because my computer is loving all of this. Yeah, sure, you can save everything. I don't really care. I have way too much open. All right, okay. So we have all this stuff here, right? And we have the ability to have records and we have all this craziness, right? We can store these keys. We have the ability to switch between types and all, but how do we use it? This is a big problem, right? So we're going to begin by using it by printing it out, right? I think it's a really good place to start. So this is where we're going to begin with a print function, right? So let me just demonstrate how we print our CSV. So the first thing we do is we set the color. This isn't a typical C function. I just wrote it, right? It uses a bunch of terminal magic. You don't really have to understand how this works. You can look at it if you care about it. But basically, if you output certain sequences to the terminal, it will change the color, right? So we're setting it to bold, black, white, right? And then we're going to add some spacing for the 0 column. We're going through all the headers, right? So all the stuff that was at the top here, right? All of these. And for every single one of them, what we're doing is we're printing out the value of that, and we're stating there's just this implicit rule that I've written so far that means everything's going to be 15 characters long. In reality, you could calculate how long it will be, but I don't want to spend that time doing it because it'll be a lot of work. You've got to go through all the rows. You've got to do like fitting. Oh, do I want it to be less? Do I want it to be more? I think it's easier for us just to set it to a constant 15. So what this is going to do is just print out the spaces before, print out the spaces after, as well as just print out the header length and cap it to 15. Okay. So let's print out our record. Again, pretty simple. We're just going through, we're printing out the number for the record, right? So it's going to print out 3, print out 1, print out 2, print out 3, 4, 5, 6, so on. And then we're going to get to this point, right? And when we're at this point, right, we want to be able to go, okay, let's go through every single column. Then let's print out that column value. So you go, okay, well, if it's a string, I can just do something like this. And this will print out my string. And notice here how I don't have to go through the column type because this was an anonymous union, right? This, if we look at it again, right, it had this no value here and no type here. It's anonymous. It doesn't really exist, right? So I can just straight go to text. But I use the underscore, so every time I'm reading the code, I know that this is a union, right? Otherwise, I don't know if this is a union or a member. It's just a style thing, right? You don't have to follow this. You can come up your own way. But the big point of this is okay. This will compile. The compiler does not care. But this could crash. And the reason why is because if I give you a number and you read in a number, you're going to try to print that number out as a string. Because what you're going to do is when you see the number 2.0, and I mean, let's actually get what the value of 2.0 is. I can demonstrate that. So this one, okay, deal, colors, let's make it nice again. We have 2.0 here, right? Let's grab the value of 2.0. I mean, this was a presumably pretty easy one to know. And we're going to check this 2.0 value here, right? What's going to happen is it's going to read this and go, oh, okay, you want to read that as a text. I'll read the value at this address. So it's going to go, okay, tell me what the address of this is. Okay, the address is OX 40,000 or whatever, right? Or whatever that value is. It's not 40,000. It's like 4 million? I don't know, 40 million. Anyway, it doesn't really matter. It's 40 million or something. It's obviously it's hexadecimal, so that's kind of a weird thing to say. The actual value of it is this, right? It's going to go to this hexadecimal address and try to read a string. But obviously, it's not going to be able to read a string because we're storing a number there. So who knows what's after it, right? So we know what the next 4 bytes is, but we don't know what's after that. Now, this will kind of work. And the reason it will kind of work is because we see if our string, let's look at the first 8 bytes, 8 bits. This is the first 8 bits. It will print out whatever the value of this is. Then what's the next 8 bits? Oh, it's 0. Okay, that's /0. So it will stop. So this will actually kind of work. It won't crash. It won't have any problems. And that's only because our double is effectively 4 characters and one of the characters is 0. And if we grab the value of this first character here, it's going to be 64. Okay, well, what's 64? We can open up our ASCII table. That's octal. I don't really want octal. Is it the hexadecimal? Sure, hexadecimal 40. Oh, it's going to be at. So it will probably print at. Just a single at sign, and that's it. Right? And we could see that if we really wanted. Maybe we do. I don't know. Maybe we'll come back to this and we'll try an example of 2 and see whether or not we get at. But for now, you can just, I guess, believe that this is going to be printed out as just at followed by a /0, right? Obviously, we don't want that. We want to print out the value 2. So how do we do that? Well, the simplest way is that we could just check what the type is. And if the type is a CSV record number, and hopefully most of you know what this is, this kind of case statement is, and I do my breaks the weird way, I know. You probably learned that your break statements go inside, and that's okay, but it doesn't actually really matter where your break statements go. See? So the way I do it, this would be text, is I always put the break statement after this, so I never forget it. It's always obviously there. It's just the way I write my code. It's a little weird thing I do. I will put it in here for the sanity of it, but I will probably forget and accidentally do it the wrong way multiple times. Okay, so here it's a number. So if we know it's a number, it's very easy to print this out. Like that. If we know this is text, again, it's very easy. We can just print this and score text, and we're done. You know, clean off your hands. You can go home now, right? This is it. And so that's all we need to do with printing. But when we want to actually like read these in and we want to set these, it becomes a bit more complicated. So let's look at that now. Let's actually look at how do we read files in C, right? So there's a few things here. And the first thing is that we have this function. This is our entry point, right? To read in the file. But before we do that, we have to initialize. And so the main function is very nice to us, right? It will read in the input, go, okay, you gave me a -f. That means then you're going to give me a file. Verify that the file is correct. If the file isn't correct, it'll give you an error, right? These things are just import things. They'll go away in a second. I don't know why they appear. And then it will, once it's done, it will have the file input. Then it will look down at the bottom, go, okay, yes, I've got a file. Okay, I'll initialize it as a file. Great. Or I've got a string. I'll initialize it as a string. Okay, great. Okay, now I've done that. I can read out the CSV. So it'll read the CSV into memory, right? And then now we have got it in memory. We've got it as a structure. And then we've got some functionality that we can do. And underneath, if we actually look what the CSV file is, it'll be in defs. We can see that CSV file is just this magical table here, right? That comment is outdated. We have, it is actually, no, it isn't outdated. It's just in the wrong place. Put it to a proper place. Okay. So we have this kind of opaque table type here, right? This table type could be anything. That's what this basically means. It's like, it's just our underlying table of our CSV file. And then we've got the headers and header length, right? But we don't actually know what this table is. This is an opaque type, right? You may have not experienced an opaque type. If you know Java, it's kind of similar to like an interface or to an abstract class. If you know Python, there's no real similarity, so I'll just kind of explain it. So we're basically saying, hey, this is a structure. We don't actually know what's inside of it. All we know is that it's a structure, and so therefore you can only use pointers with it. Because that's all we know. So we can take an address to it. This is fine. But if we did it like this and we try to compile, it would give me an error because it says, hey, it's incomplete. I don't know what's inside this, so I don't know how big this structure will be. If I don't know how big this structure will be, then how can I do anything with it? How can I allocate it? But if we make it a pointer, since pointers are always addresses and addresses are always 8 bytes, it doesn't matter, right? We can always have the same kind of thing. This can go away. And so it's, again, it's called an opaque type, or it's sometimes like an inherited type in some ways. And so, for example, this is our table. And you'll notice here in our table, we don't have anything we find, right? This is just a generic table. Yep. We have the ability to index our table. We have the ability to remove columns, remove rows, insert rows. We have the ability to initialize the table. Then we have this really weird apply function. We'll go over that later, what that does, right? But that's effectively enabling us to pass a function into another function. So you can pass a function by reference, basically. And so what that means is that you can use a function like as a variable. It's really, really awesome, really, really useful, and can really make code really clean because it means now I can do anything to my table without having to like build this big iterator that goes through all the indexes. I could build a big like for loop that goes through all the indexes, or I could just give it this map function and it will just call it for all the indexes, or indices rather. And so yeah, let's look at what an implementation would look like. So for example, a linked list. Now, if you've never seen a linked list before, hopefully you have, but let's just give you some vision of it, right? You basically, a linked list lives on the concept of an array, right? So an array, you have a sequence of values in contiguous memory. Contiguous meaning that the memory locations are placed one after another. So it means if I have the memory location of 1, I can also grab the memory location of 2. They're concurrent, right? They're contiguous. They're right after each other. A linked list extends this and goes, well, okay, sometimes we want to resize this array. Now, one thing that we could do is we could just literally resize it. We could go, okay, use something like realloc, as you maybe learned in the cheats, or which is basically realloc is just the same thing as kind of like doing a free followed by a malloc. There's a slight difference between them. The big difference being that realloc doesn't actually always free the memory. Sometimes it can just expand the memory, which is one of the reasons why there's a lot of bugs with it. And one of the reasons why I always recommend, especially when you're beginning, to actually just free them remalloc, right? Well, rather it's going to be a free. Instead, the order of it's actually going to be a malloc, a mem copy, then a free, right? You malloc your new memory, you mem copy it across, then you free the old one. And especially when you're beginning, just doing that kind of pattern, maybe making your own function to do that is a little bit easier than using realloc, because otherwise the problem is with realloc, you can still use like the old pointer value and it will probably still be okay until it can no longer expand the memory. When it can no longer expand the memory, it'll free that chunk, grab a new chunk of memory, and with a different address, which means that all your code will suddenly break at that point, which means it may work on your computer. You put it on the CSE computers where there's more fragmentation or whatever, right? And then expand the chunks, which means that you basically will end up with I mean, it's hard to expand chunks, which means it'll be free to mallocs.
Hey, Braden,
Yes.
can you just confirm when do you actually use malloc and when do you not have to use it?
Yes. So I've actually got a really good example, and I'll go for that in just a second, about how much basically you should avoid it as much as you can, right? That's my tip, is avoid it whenever you can and only ever use it when you really need to. And I'll go through that right in a second, right? So actually, let's just go for it right now. Let's just jump right into it, and then we'll come back to the linked list because it's a good segue. So we have all this memory here, right? And we have this reader. You notice I haven't allocated the reader. I always pass the reader by reference, right? I go, okay, give me an address to where the reader is, because this thing requires a pointer because it wants to be able to edit this. That's all it wants. It just wants to be the ability to edit this reader, to initialize it. So we pass it by reference. Another thing we could do is we could make this a malloc. So I don't. Malloc, right? But why don't I? And the reason why is because I don't need to, right? And so the reason I don't need to is because of lifetimes. So what I like to do, if you're kind of new to lifetimes, is you put a bunch of extra braces. Your code will still compile with them, right? And you put braces surrounding the lifetimes of all your variables, right? So what this means is that this reader is going to exist from this point to this point, which means as long as these functions I'm using it in are only within these braces, I'm okay. As soon as I want to use it down here, it's already gone. I can't use it anymore. If I try to access reader down here, it will give me an error. So yeah, it's not even in the list. I don't know, undefined. Sure, right? I can't access it because the lifetime of that object is gone. It's dead. It's been thrown away in the trash. And so you want to use malloc when you go, okay, I don't actually know when it's going to end. So for example, this CSV function, we don't know when you're finished with CSV. We legitimately do not know. You could be finished with it now. You could be finished with it in 10 minutes. You could be finished within like 3 hours. We don't know when it's going to end. And so for that reason, we can return a pointer to it, right? And so that's often what you would have done in probably most courses, right? Is that you would return a pointer. And you go, okay, I'm just going to return a pointer to everything. It'll be okay. In this, we don't need to, right? And so we want to basically, the answer is just restrict as much as possible. Never use it until you have to, right? And so unless you know for certain that you can do these braces around your variable and it will encompass all of its uses, you can't use this. So for example, for linked list, right, you have to allocate the linked list elements, right? Because for each of the linked list elements, you don't know when they're going to be freed. And not only that, you don't know what order they're going to be in, right? And so it's not like you can just say, okay, create me an LL. I don't know, this is my linked list, sure. And this equals, and then I've got a next element, right? And this equals another LL, which is another next element, right? Now I could write it like this, and this would be mostly okay, right? But all these elements would have the exact same lifetime, right? Because they all would have to be created at the same time, which means they're all going to go away at the same time. Using this.
Broden,
Yes.
with regards to that, in the lab exercise we had last week,
Mhm.
there was a function there with regards to the bit ops and all that sort of thing, where we we didn't have to allocate memory, even though we created within the function.
Because you were returning it from the function.
Yeah, so
So
you're returning the value or a struct with three components in it
yes.
from the function. Why do we not have to allocate memory?
Okay. So the reasoning why is a little, it's not necessarily complex, but it revolves how like the stack actually works, right? So when you call a function, what happens behind the scenes is the computer goes, okay, you're calling the function foo, right? Or let's say you're calling function get float bits, right? What I'm going to do is I'm going to allocate space on the stack for this function, right? So an example would be I'm going to allocate space for the variables, right? So maybe you've got like a variable inside of this, like your uint or something. You also have, for example, maybe another variable inside of this. For example, your return value, right? As though you had, right? You had this kind of weird return value thing that would say, okay, this is my return value, and it can holds all the float bits, right? Um, and this is on the stack, and this will go away when the function returns. Now, but how does it work? How can you actually return this value then? And the answer is that C is a little bit smarter than that, right? So what it will do is it will go, okay, you want to return this value. So for me to allow you to return this value, I can't fit it in a register. You've learned MIPS, right? You learn how registers work. You learn that you have, or basics of MIPS, you know, there's a return register, hopefully, right? If you don't, you'll learn very soon. And the return register stores like the result of the function. I can't store this return value in that register at all. I cannot. There's no ability for me to. So what it will do is it will instead store that return value on the stack, right? And will instead like basically put a pointer to it, right, in the register. And so effectively what it's doing is it's kind of pulling that variable up, storing that variable in the parent rather than in the child. So effectively, you know, I don't know, I'm just gonna call this main, right? What's happening is that main is allocating return value in its own stack frame, right? And this is not allocating return value. And this is just using the return value from the previous function, effectively, right? And so you're ending up with an extra amount of space. And the reason C can know how to do this is because it knows that it's too big to fit in a register. So C goes, this is too big to fit in a register, so I'm just going to use the stack, the top value of the stack, right? And so there's other ways it can do it too. For example, it could try to put the return value at the very top here, so that when it drops values off the stack, it will just drop this stuff off the stack, and then this basically gets concatenated up into main, or it will allocate in the parent. Does that make sense?
Sort of.
It's kind of like the way it works is that it can't return it directly, right? Because it's too big. So it stores it just in the stack like a variable here, right? And
Yeah,
then whoever calls your function knows that it's going to be on the stack.
yeah, I just can't understand why a function you would create a pointer and malloc it, where in
Yeah,
some instances like this we don't need to when it's allocating a value onto the stack and then the main function's referring to
that's
that
a very
address
good
and
question. And the reasoning why is completely depending on how you're going to use that value, right? So for the example with the CSV here, I probably don't have to allocate this. I could decide not to, right? Because if you actually look at the code behind this, I don't really know what this is going to be. I could make this just a normal value and I could just return a structure, right? But the other things I need to handle errors as well. And so for me to handle errors, a simple way is for me to just return null. And so in this case, I'm using it as a way to mark null. I could also have like, I could also require you to actually do what I did up here, right? Where you pass it by reference. And so you create your own CSV variable, this, and then you'd pass it by reference in the next frame, and you could have like if check on this, like this would return a Boolean instead, right? And that could also work. You know, there's a lot of flexibility in the system, right? And the reason you return sometimes a malloc and sometimes don't return a malloc is completely dependent on how you're expecting people to use it. So with this linked list here, right, when you want to grab a table index, you want to be able to edit that table index in the original place that that element was allocated, right? You don't want you don't want to edit a new version of that. So in that case, we want to return a pointer to it so that you edit the original record of it. So if you go and change what this record's value is, it changes it for the entire table, right? It doesn't just change it for your version of that record. It's a committing operation. And so with a linked list, right, we would want to return a new pointer to the linked list elements every single time because we want to be able to modify this object, right, and have it consistent across all. So we may have multiple next methods pointing to the same linked list element. It's kind of cool, but you could have like one, you could have two, and you could have both of these pointing into the same value. This could be a valid case, right? You could also, which is the same, like kind of like a graph if you don't do 521. The other case would be that you want to actually move values around. You want to move the head and you want to move the tail around. You don't know how big this type is going to be, right? You don't know how big this recursive type is. So if we make these non-pointers, what it's going to try to do, right? Inside, oh wait, that's the wrong place to put it. If we make these non-pointers, right? It's going to try to fit a linked list inside 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 a linked list, right? Because we don't have a chance for it to be null. It always has to exist. Each of the structs have to exist. And so the size has to be infinite because it has to store for every linked list element, right? I guess I can show an example like this. We'll have another element for next. And then that element will also have another element for next. We'll also have another element for next, right? And this will have to go on forever because I don't give it a point to stop. And so we make this a pointer to say, okay, eventually this can just be X or null, rather. And so there's two cases that we want to use it, right? One case is when we want to have conditional, when we want to have it, it may exist and may not exist. Same thing with CSV, right? This may exist, this may not exist. So it's a conditional value, right? That's one really useful case. If I'm extracting the float bits from a number, there's no conditional case. I'll always get those bits. And so there's no need for the pointer, right? And also when I'm returning that, and you're going to be editing that pointer, there's no original source for it. There's no original place it's going to be stored. So there's no need for that pointer. So you only ever need pointers in two cases, right? One, when you want to edit from multiple places, right? So you need like a single source or address rather, right? Or two, when you want to have like an optional value, right? So it may exist or it may not exist. Those are the two cases.
Hey, Brayden,
Yes.
if you malloc something within a function,
Yeah.
and the function ends and all the variables and things that are created within that function disappear,
Mm-hmm.
do you have to free the memory? Or if you forget to free the memory, will it actually just disappear with that function?
No. That's the whole point of malloc, right? Is it
Okay.
doesn't. Because if it did disappear, then you could never return it, right? Because it would be gone.
I mean, after the function's finished, if you just happen to create a variable and you malloced it within the function.
Yeah, I get what you're saying. Yeah, yeah. So if you did that, C can't tell whether or not this variable is used elsewhere. So if I just did malloc, whatever, right? And then down at the bottom, I didn't have return. I just had like a normal return here, like no return X or anything. In C's mind, that this memory, it doesn't know when it's going to end. Even though we can probably see that it should be ending here in this function, I just forgot a free, right? C doesn't see it that way. C just goes, well, I just see a single malloc and I just see a single free. You're asking for a memory here, you're releasing memory here. So if I remove the release, it's never going to release.
So number one rule is if you ever use malloc, make sure you stick the free in underneath.
Or make sure there's a free somewhere. So like a linked list, obviously it's going to be freed somewhere else in your program, right? So for example, let's say we want to remove a row. I'll just start writing I'll write the edge cases, right? So obviously we can't remove the 0 row and we can't remove the top row, right? Because in our program CSV files, in Excel, this is 1, not 0, right? It starts from 1. It's 1 indexed. And then we could just do some point of arithmetic here, right? So we're going to grab the head, right? And we just want to iterate through one by one. So this is presumably, you guys seen this before. This is fine. This is hopefully okay. And basically just iterating up into a row, right? Up into the row that you want to remove. We're now at the row that we want to remove. And then we can just go, okay, if a row exists and that row has a value, right, which is going to be next, right? We're stopping just before it. This is the thing with linked lists, right? You always want to be on the previous element. You never want to be on the current element. This will most likely run a few minutes over time. Then what we want to do is we want to remove the next element. So we can just remove it. Right? And then the easiest way to move it is just to link up pointers, like ditch them, whatever, right? You just kind of like removing it by going, okay, if we have A to B to C, right? We're going, okay, we want to remove B because this is current next. What we're going to do is we're going to say, okay, now A points to C. What are we doing? We're just going, okay, this is going to point to this. So no longer do we have a reference to B. It's cut out of the wheel, right? And then all we're going to do here is just we have this remove variable, then we're just going to free it, right? Now, one mistake that people make is that they will try to free it before.
Where have you actually allocated the memory to free it?
I have to do that in when we insert. Right? This is the whole point of it, right? Is that we don't know when we're going to free it. We don't know when we're going to malloc it, right? So that's the utility of pointers, is that we don't need to care, right? We can go, okay, we want to remove this. So let's free it when we go, okay, remove. And then when we want to insert, that's when we can malloc. We can do them in different functions. We can separate that behavior across our program.
Yeah, right.
Which you can't do with stacks, right? You can't do with a stack allocate memory because they have to be within a function. You can't separate across functions. Okay, so insert is pretty easy as well. Obviously, if we want to insert at the very first element, we want to insert after row 0. Keep in mind that we don't really have row 0, right? Row 0 doesn't exist. Row 1 is our first row. So if we want to insert after row 0, we're basically saying insert before the first row. So we can also do this, right? So we can say, hey, allocate new. This is a trick. It's basically we'll calculate the size of new because it goes, okay, dereference new, then give me the size of that result. So the dereference new is going to be this, and the size will be LL, right? So how big is it in bytes? Okay. And then we're going, okay, new data equals record, new next. This stuff is reasonably straightforward. The big thing here that you have to realize, obviously, that we're using the pointer here to indicate because it's a pointer, right? So we have to use this kind of stab symbol because we have to dereference it. Behind the scenes, it's just doing this, right? But we can simplify that to just using the okay. And then we can go, okay, if we don't have a head, then we also didn't have a tail, right? And our head will always change. And so we can think about this as, okay, we've got two cases. We've got the cases where everything's empty. In that case, we want A, and we want this to be both the head and the tail, right? If everything is empty, this is going to be null. This is going to be true. So therefore, it's going to assign the tail and the head. Other case, we do already have an element, right? We're going to go, B next equals A. A already existed, so we don't set the tail, but we always set the head. Okay, wonderful. Table init function's very easy. Oh wait, we won't actually finish this. That's right. We got to go do more work. So it's just same behavior. We're finding the previous element. That's all it's going to do is find the previous element, and it's going to put after not row. Okay, we found the previous element, so we can go. Okay, if current equals null, or current next does not equal null, or current next equals null rather. And what we're saying is, okay, this doesn't exist, right? There's nothing after this element, so this has to be the last element. It has to be the last element, so we'll add it at the last element. This is where our malloc is going to come in, right? So we can malloc a new element up here. I guess we're always mallocing, so why don't we just do up here, right? Save us a bit of time. So here we can just say new, I guess next is going to equal null, right? There's nothing next after it. This is going to be the last element. And then we can say something like table tail next equals new, and then table tail equals new, right? So what we're saying is we're going, okay, what used to be the last element is now going to point to our new last element, and then this is our new last element. So if we show it out, right? We want to add D, we want to add it at the end. So what we're going to do is we're going to place D here. Then we're going to go, okay, what used to be the last element C is now going to point to D. And then we're going to change what our last element is. Or a tail. It's like a tail of a snake, right? Okay, and then we'll just do the same thing here with, I guess we can just say new next equals current next. Then current next equals new, right? And this is the same idea, right? Where we're doing something like this. We want to insert it after B, right? If we want to insert it after B, then what we want to do is we want to go, okay, chuck here, right? And then we want to do this link here. We want to grab this link, and we grab this link value from what B used to be linked to, which was C, kind of like this arch here, right? Okay. So that's going to link up all our data types. That's good. We're happy. We've got our function. This is good. So we're basically almost done, right? All we have to do now is just read the file in. Now, I'm not going to do strings. I'm always going to return false here. I will include some basic string code for how it works, because the string code is going to be very similar to the file, right? It's just whether or not you're reading from a string buffer or a file buffer. But I think the file buffer is more interesting here, and the code's so similar, so it's a waste of time to do both, right? So let's begin. And the easiest way to begin is probably to read in the headers, because sometimes there could be headers, sometimes there could not be headers. So what we're going to do is we're going to grab what were the headers here, and we notice that from with this function here, right? In this function CSV init, we've got to call this at some point. This is going to initialize our CSV file. And we've got to give it all the headers, right? So we've got to give it some headers. So how do we do that? Well, the simplest way would be to just basically go, okay, we probably need to define buffer size. I hate that name. That's fun. And we can just create this like line buffer that we use like fgets, right? Over. And we go, okay, so we're initializing this reader here, right? And we want to do a reader, and we want to read each of the lines. But the thing here is that we don't really necessarily want to initialize it here, right? We're just basically telling the system, here's a reader, it's going to read a file. That's all we're actually doing here. So we're not even going to do this yet. We're literally just going to say, okay, we have a reader. So let's begin by zeroing out a reader. So this is a trick to zero out the reader to basically set everything to null or zero, right? We're going to say set everything to zero being the size of this, right? So just going to iterate through and set all the variables. Because we have so many variables here, we really should just set everything to zero to begin with, right? Okay, next thing, we want to set file. So we can go like, hey, grab the read mode and tell me the file buff, and I'm going to set this to file. This is going to go, okay, I'm now in file mode. Then we're going to grab the config flags. Right? We're going to just move over the config they give us. Right? And then we're going to grab the config, grab the flags, and we're going to and equal to basically say, hey, this thing is definitely not in string mode. And that's what we're basically doing is if you somehow pass it in so it's in string mode, we're going to turn it off. You asked it to be in file mode, so it's always going to be in file mode, which means that has to be 0, right? So if we look at what this is going to be, I don't know what the value of this is. What is it? It's 16. Okay. So if I go here, here, I do not 16. This is the value of not 16, right? So basically everything but this one bit will be set. So it doesn't matter what the value is. This is an and, right? So for example, if we have, let's say 16 and, or I don't know, 8 or 32, and we and this with not 16, right? We see, okay, we have 16 or 8, right? Or 32 because 56. So this first value here is going to be 56, which is this, right? And then we're going to grab our value of 56 and we're going to AND it with not 16. And you notice that this was our value of 56, right? Which was this. And when we AND it with it, we only get the bit that we want, right? So we only get these two bits set. We're purposely always forcing this bit to be false. These bits don't get set, right? Because they were never on. They have to be on both sides. So the basic idea is that, if you want to toggle something, you use this. This toggles it on and off. This basically can be used to turn something off with and this can be used to turn something on with this, right? So there you kind of get 3 options. Okay. But then we can go, okay, if we have some flags and we have the flag that says we want to use a defined header, right? Basically, hey, if this flag is true, if well, it's not the fourth bit, right? It's going to be the second bit, 0, 1, 2, right? Rather the third bit, but the second index of the bit is going to be this one here. If that bit is set, then what we want to do is we want to say, okay, grab the CSV headers, and you can just grab them from the config, right? Config that's passed in, there's your headers, and you're done. And we can just return true. Okay, great. You write some reading code. Okay. We can use what we had before, which is our headers down here, right? So we've initialized our file reader, we get given our file reader here, and we're all good, right? And we can initialize our headers. Everything's looking up good. The problem is that we don't actually know if this is file or not. So what I'm going to do here is I'm just going to check and make sure it's file. How do I check and make sure it's file? Well, I basically just use the exact same thing I did before, right? Config.flags and CSV headers flags of string mode. Basically going to say, okay, this thing can't be set. I'm going to say, make sure this is the opposite of this, right? So this is false, right? The other way you could say if it is in string mode, return null. And we don't support this currently. Maybe you're doing printf error. We don't support strings. Okay. Now we have a line buffer. How do we read in C? Reading in C is pretty easy. We have two tricks, right? And the first trick is going, okay, may or we may not want to be able to have to read the first line of memory, right? We may or may not have to go and do a fgets, but we have to know whether or not we have to. So we can go, okay, if we has headers and for some reason this probably doesn't have to exist, we probably could figure it out from just the reader data, but sure, it's been given to us in this case. So we can just check if this has headers. So we're saying, okay, it doesn't, or rather, it should probably be has headers, right? If it has the headers, then we have to read out the headers. Okay. And if we're doing it that way, then we probably want to switch this condition here. Okay. So we're saying, okay, it has headers, right? And we want to read out all these headers. Well, we can just do an fgets. Right? Read mode, file buff. There we go. That's our fgets. It's going to read for every single line, or in this case, just one line, but we can put in a while loop to read for every line. We grab our headers out. We can use a string dupe, right? This will just allow us to modify the headers, which is important because we need our own copy. This is the other thing. This string dupe is a malloc, right? Why are we mallocing here? We didn't malloc here, but why are we mallocing here? Well, the answer is that this headers is going to have to be edited by the system, right? Our CSV, when it initializes, it requires the ability, actually, it makes its own copy, doesn't it? So maybe it doesn't. Yeah, it makes its own copy as it goes through. So it is probably doesn't have to be malloced. So we probably can get away with not mallocing it unless we wanted to reuse this line buffer. If we wanted to reuse this line buffer in a while loop down here, which we probably do to read out each of the columns, or to read out each of the rows rather, then we would have to malloc it, right? Because we would want it to be reused. And so we can't have two variables trying to use the same bit of memory, right? Otherwise, they're going to conflict. Okay, so we just grab the length of this. I'm just going to trim out any of the new lines. Because obviously if there's new lines, I don't want them to appear in my output. So I'm just going to trim them out, right? And you've probably seen this trick a few times. We're basically saying, hey, if the string ends with a new line, make it end with /0. And /0 in C means the end of a string, right? It's the terminating byte. It says this is where the string ends. There's no such thing as like headers.length, right? This is a pointer, it's just an integer. To find out the length, we have to count all the characters. So we can begin, we have our headers now, we can just initialize our CSV file. Okay, great. And down here we can return it. Now let's count through all of our buffers, right? So this bit is luckily not too bad, right? We just have to basically do a counter. So hey, while we can read the next line, because we've got to handle EOF, right? And we can go, okay, read from this file. Again, this is pretty similar to what we had up here. This is just the file we're reading from. I mean, we probably could just call it file instead of file buff. Do that. dot, I think call it dot file, then do pointer file buff. Okay, and I did that one. I can fix that. So I'm just replacing everything in file. It just makes it look a bit nicer. Okay, so we're going through and we're reading each of our files. That's okay. Nothing's crazy here yet. But then what we can do is we can grab the next column, which is going to begin with line buffer. And then we can go, okay, at some point, we're going to have to grab where the next comma is, right? But before we do any of that, let's make sure that we trim all the white space. Now, I don't want to trim the new line yet, right? Because I want to check for the new line. Check new line actually matters to me. Okay. Okay, if current color equals new line, this indicates an empty record because this means there's nothing else in that line but new line. So we can check whether or not we want them to skip empty records. We have this ability, right? Okay, if our config flags, if this is set to be, I don't know, what do I call it? Skip empty lines? Sure, that's right. If we're going to skip all the empty lines, then yeah, sure, skip that line. It's just going to skip it and read the next line. Okay, great. But then I can go, okay, give me the length of the string so I can trim from the other side of the string. So I can go, okay, you know, if it ends with any new lines, any spaces or anything like that, we can trim them. Probably won't trim spaces, just it's no real need, right? Take a bit longer. But we do need to trim the new lines, right? Because we don't want new lines showing up in our output, otherwise our table won't look right. Okay, then we can go, okay, how do we check whether or not it's empty? Well, the simplest way we could do it is the simplest empty string has to have a comma for every single row. So for an empty record, it has to have at least one comma for every single column, right? -1, I guess. So in this case, we've got three columns, so therefore there'll be 2 commas. So we know this is an empty record if there's only 2 items. What we can do is we can go, okay, if your length, right, of your current column, I guess in this case is going to change, so we probably should the length minus, right, so have the right length. If the length is going to equal the CSV header's length, right, -1, so we're going, okay, if the headers that you have, if you have 3 headers and you've got 2 commas, therefore you must be done, right? It must be terminating. Or that must be an empty record. We can go, okay, give me the empty record, skip empty records, sure, that's fine, and we're going to say this is equal to a CSV flag, skip empty records, right? Now, one thing you notice here that we did it differently is that we have to say this is equals. And up here we said skip empty lines. But remember, skip empty records, they're not always just records. They could just be empty lines as well. We also go and skip those. And so the difference is up here, we could just say skip empty records. And we don't need the equal sign because empty records is made up of also empty lines. So we don't care which of the 2 bits is set. We just want one of the first 2 bits to be set. That's it. If one of them is set, it means it's either empty records or empty lines. Or it could be 1, I guess, but 1's not really a valid value. Like you can't configure 1 in our program. We can just exclude that. Okay, so in this case, we also want to continue. Wonderful. Okay. Next, we can read off our columns. And you notice that we're doing something a bit different here, right? So we're just going to first allocate our columns, and then we're just going to read all of them, right? It should be record. And why are we malloking here? Well, because we don't actually know when these columns are going to be freed, right? So the columns are going to have to sit within our data type, right? Within our, I guess you could say within our record. And we don't know how many there's going to be. And we don't know when we're going to free it. We don't know any of this information. So we're going to create an array because we need multiple of them. And we don't know how many there are. So we can't just create a VOA. Okay, VOA, this would go away at the end of the scope, right? So we need to use malloc because we want an array. Okay, and then we're going to go this. All fine. Okay. But then what's next? What do we do next? Well, we can basically just, as I said before, we can just iterate through, right? Life's not too bad here. Okay, iterate through all the elements one by one. right? And we're going to go for each of the columns while there's a next column. But we don't even know what this next column is yet. We're going to figure out what the next column is now. So the first thing we want to do is if the current column, if we begin with a comma, we want to skip it, right? Because obviously, basically how we're going to separate this out, right, is we're going to read this in, and then we're going to go, this is the first element, and then this is going to be the second element, right? And this is going to be the third element, and so on. And so we want to skip them if they include that comma at the start, because that comma at the start is not important. So we can just go saying like, I don't know. Yeah, sure, that's fine. We can skip it like that. Okay. Then we want to grab I guess we just want to find the next comma. So we're just going to find the next comma. And so the trick is you think of string. This is a function inside the C standard library, right? And sometimes if you don't know what functions exist, you can just Google it, right? Find out what functions exist that you want to use. String, we would find out where this string is located, right? So it's just as like a match. It just finds the next location of this within this string. But here's the weird thing is I'm moving the string along. Where's my indices? I don't have any indices. It's all pointers. I'm just moving my string up and down. It's almost like a view, right? String looks like this, sure. And I have my view here that begins here. And I'm moving this up and back down again, up and back down again, right? And I'm looking for the commas. Every time I say a comma, I go, okay, this is great. I want to stop here. This is my next section. That's going to be my next section. And then I can just, you don't really have to care about what this does, but I'm basically just going to try to convert it to a number. And if it doesn't work, I'm going to go, okay, yeah, it's fine. So let's just convert it to a number. Yeah. Not about that yet. I don't know if I want to skip spaces yet. Okay, so what we want to do here is we're going to go, okay, this is convert to a number, right? To a double, so string to double. And then we want to go, okay, we've got this end pointer, right? And we want to find the actual end of this pointer. So for example, if we have the value, say 20, right? And we want to pass this, our end will be pointing here. That's the end of the match. If we have the value A20, our end will still be pointing at the beginning. What we want to do is we want to keep finding the actual end because there could be extra like spaces and various other things, right? That's what I was writing here before is I was trying to skip the spaces, but I didn't know if I wanted to do it yet. But yeah, I do. Otherwise it won't work. So that was skip through spaces one by one. Now that we've skipped all the spaces, then we know they're truly at the end. We can check what the type is. So this will return in this end value. You can look at the docs for it. I don't know. Man, string Todd. Look down here, you can look for the docs and you go, okay, these are the values, and eventually it will say somewhere here, right? So it's going to return the value stored in that pointer in either two cases. If no conversion is returned, it returns 0. We don't care about the return value because it could just return 0 normally. But it will set end pointer to be the value of end pointer, right? So it will send end pointer to be the value of end pointer, right? So this will point to this, which is what we're checking here as well, right? Okay, so we've checked it, and we're going, okay, this checks, okay, it could be a number still, because the pointers still match, and I don't really know what else I want to do. I guess we got to check ends right. Yeah, sure, we have to check it. If it ends with a /0, that means it's also ended. If it ends with a comma, that's also fine. Is there anything else I want to do? Oh yeah. If the config flags, if those are string mode, I also care, right? So that will also say this thing has to be a string. But if I do it like this, I'm going to say it has. If it's a string, I'm going to convert it to a number, which is wrong. Instead, I want to say probably it isn't this, right? So this isn't true. Okay. But in this case, this means this is going to be a number, not a string. So it's going to say columns of column dot type equals CSV record. And columns of column dot number equals try num. We're placing this number inside this union, right? This union. I don't know, I can't pronounce it apparently. And we'll probably need some kind of column type. I don't really know where I want to put this column type or what I want to do with it. But I'm just going to create one up here for now. I'll just call it an integer. That's fine. We'll figure that out in a second. Okay. And then we want to find and we want to go through each of these and we're going to go, okay, give me also the type for the string. And once we've done this, it should be number. I just number, then wrote text. Right, there's a text. Okay, then we want to find out the end of the string. So now we want to copy the string just between the starting position and either the /0 or the comma. So we can go, okay, the end of the string will either equal whether or not there's an x. If there is an x, it'll be equal to the next comma. If there isn't an x, it means there's no more commas left, right? And therefore, we basically just want to find the end of the string. This is, again, pointer arithmetic, right? We could rewrite this. This index of string length, right? But we can just say go to current column and move that many characters forward by this. So that's how many characters we're moving forward. Remember, if this was an int, it would move this many integers forward, right? Pointer arithmetic moves based on the base type. Let me just do something like this. That's fine. Equals malloc. We're just basically doing a string dupe, right? But we're doing it by hand because we want a specific range and it's a bit easier to do it by hand. So we're just going to do a mem copy afterwards. We're going to copy this much memory into this text element from current column, and the amount we're copying is this, right? So we're saying this is where we're ending, this is where we're beginning. So the difference is going to be how much space we want, and then we're adding 1 for the /0 at the end, because every string needs a /0 to determine its ending. And we're going to do the same thing here. Okay, we're so close to being done with this part. And I probably won't run too many more minutes overhead. This one did run over because I did expand the code for a while. We did talk for a while. We probably took 30 minutes before we started. Okay, and then we have this thing here with the CSV record. All right, where we're going to say this is our record that we're actually going to create. And you notice here, I'm not creating this on the heap. I don't need to create the record on the heap. Because to create the record on the heap, that makes no sense because I'm immediately going to put it inside a linked list element. And if I'm immediately going to put it inside a linked list element, its scope is going to be from here, here. Right? Because as soon as we use it, we're going to immediately go insert into the row, insert into the table at this row. Count doesn't make sense. I don't know. Do we want a counter? Probably. Oh, we got a counter. Okay. Sure, we can put count. And then we want record. Right. And so we're immediately going to use it here. So there's no point doing anything else with it. So we can just go, I don't remember what I call them. Row, I think. Who knows? We'll just guess row. The row is going to be count plus 1. Remember, we're starting from 1, not 0. The columns we just can copy across. I think it's called num column. Find out in a second. It's no, is it called num columns? It is. Okay, wonderful. Okay, and then we can just increment the count at the end, right? Because that's the next element done. And we're done. That's it. So this function, it's pretty short, right? If we break it down to it, we're grabbing the headers, then we're grabbing the fgets, we're verifying, and then we're splitting up based on columns, and we're going through every single column by finding all the spaces with the commas, right? So strings are just arrays of characters, right? We can just treat them, we can slice them up, we can cut them, we can split them, we can do whatever we want with them, right? There's this flexibility. And then this, at the end of this, should be basically be done. Like there's nothing else we have to do. We've got this printf function that prints out correctly, so we could just go and test it. Let's go and test it, right? But to test it, we need some way to compile it. So we can use this program called make. How does make work? Well, make is pretty awesome. So what make does is, if we look at our make file here, it starts with a capital M. You saw this in the lab, so I would go over it. Is we can define our compiler. So this could be DCC if you really want. DCC could be whatever. You define your flags. In this case, I'm saying I'm using C11 and I'm using ggdwarf is just because I'm on a Mac. I want debug symbols. So I use ggdwarf. And then what you do is define a bunch of rules. So the first rule I have is, for example, CSV here. this defines how to create the CSV executable, something I can run. It says, hey, if you want to create the CSV executable, this line probably looks very similar to you, right? Hello. If you want to create this executable here, then what you need is you need all these object files. So it goes, okay, how do I get these object files? Oh, this is how. Okay, so color.o is color.c. CSV.o is CSV.c. So you're mapping all these files to each other. I believe you don't need this, but we just add it for standards, right? It's just for like flexibility, because later on you may want to go, this also requires this other file, like add extra files to it, compiling them all together. So if we run make here, I think you saw, you can see it compiles color, it compiles CSV, it compiles all this, and then compiles them all together to form a single CSV. And we won't do this, we'll just do a normal CSV file example, sure. And we don't have, well, it's pretty close, but we don't have animal and we don't have type, but we have age here, right? So for some reason, it's just not reading the string. Okay, that's not too bad. We can fix that, right? So we can go, okay, well, where's our reader? Okay, here's our reader. Let's go find where it is. Okay. We are setting it as text. We are malloking the memory. Okay, everything else looks pretty okay here. I can't necessarily notice anything that's wrong, right? But here's the thing is that it could be that this is always true. You know, that could be one thing that could be occurring. So we always force everything to be a number. That makes sense, right? Because it is 0 and this will return 0. So we can look at this condition again and go, well, what's wrong with this condition? You know, and so we go, okay, well, the thing that must be wrong with this condition, right, has to be, well, okay, we have this reader here with this conflict flags. And I'm going, okay, the flag that we want to be set is string mode. If string mode is on, we want to force it to be text. So what we're saying is this has to be 0. But this should be 0, right? We would expect this to be 0, right? So we can go, okay, we could check this as 0. It probably is 0. And we go, okay, what else is here? This here. We're saying these have to be and. Well, it can't be both /0 and this at the same time. That seems a bit odd. So I guess it's got to be or. That doesn't seem like it would fix it. Right? That seems like it would make it worse, or I guess make it work less. But we can see if that fixes it. Oh yeah, it doesn't really make a difference. Okay, well there must be something else, right? And so we got this. This is fine. We're skipping white space. That's okay. We could start printing out values, start figuring out what it is. It must be something pretty small. Or it could be something to do with this. Okay, well, let's say it's something to do with this. Let's print out what this value is. Right? We'd expect this value to be, right? For this value to be true, right, we'd expect this to be 0. Right? We want this to be 0 always. So if we go, okay, let's run this. It's gonna print it above it. Oh, it's always 1. Well, that's a problem. Why is it always 1? Well, we can look at the string mode. It indicates that the reader was initialized with a string. Huh. Well, for one, this flag is actually not the one that we want. For one, the flag that we actually want is all strings, right? Okay. But for two, it seems to be initializing it with a string mode when we don't actually have a string. Okay, well, it's still all 1, even with flags or strings. So what's going on here, right? And the reasoning is that, okay, we're saying not this, but not this is going to be true. Because, for example, if we have 0, 0, 0, 0, 0, and we AND this with 0, 0, 0, 0, 1, we get 0. Pretty unusual. But then we're using this not, which is basically going to flip it to a 1. Rather, what we want to make sure is we want to make sure that this is not equal to strings. So the way we can do that is we can do this, and we can say it does not equal 4 strings. And so by saying, we're saying that this flag is not set, by saying it does not equal this. You can't use like nots and flips and stuff like that, right? Okay, we make again, we run again, and you're giving me the same thing. Does not equal. That should be fine. We can print it out to see. There's no reason why that wouldn't work. I mean, we can make sure it's just that. I'm pretty sure it's just that. That doesn't make sense if it is anything. Oops. Run. Yeah, it is that, right? Okay, great. So what was the value here? I was going to add this bit. I added this bit last minute. It's fun because right, and we can look at it and go, oh, it's still 1. Why is it still 1? And the answer is because it does not equal it. That's okay. So the thing is the problem here is that we're trying to force it. And so of course this is not going to be true. So basically we're thinking of this as a binary statement. We're thinking of this and we're saying this thing has to be either true or false. The answer is it's not necessarily true or false. Instead, what should happen is if this thing is true, then we want this if statement to be false. So we want to say, hey, if this is true, flip it. It's a bit interesting, right? Pretty sure. Oh, I cannot do binary arithmetic in my head apparently. So if this is true, it's going to be this. This is a weird statement. I'd probably rather just like flip these two, but I will try to get it working like this. So we want this to be false always if this is true. And if this is true, oh, then it will always be true. That's not, okay, we do have to flip it. It doesn't actually make sense other than any other way. So we're just going to flip these two by just adding this as an else tag. Because otherwise, the problem is it's thinking as like a binary. So it's going, okay, either your record or your number. And this is basically what this thing is saying, right? Which is not really correct. So instead, what you want to do is we want to say, okay, we can use the same logic here, but we want to flip this. So we want to say, okay, this equals current column, or end is not true, or end does not equal this, and it does not equal this. And so we're just flipping this. And this is a good exercise. I actually want to include this because I want to show that you can kind of flip things pretty easily, right? When you're flipping statements like this, because sometimes it won't make sense one way, you just got to flip the signs. I flip this to not equal, equal, whatever, and then just flip this to and, right? Or. And this becomes an and. Or. That's the problem. You would originally think it would become an and, but it's not. I bet you if this was an and, it would work too. Now I'm thinking about it. It probably should be an and. Anyway. And then in this case, we want to check that this is true. Right? So if this all flags or string thing is true, then we'll get it. We got to make it first, otherwise it won't work. Yeah, it works, right? So we can see all our data there. It all looks pretty good. Everything's pretty nice, right? Let's trick you away. Does that make sense? Do you have any questions about this part? Any questions about, I don't know, specifically about the string stuff we're doing here, about the flags? This is all making sense. Everything is not pretty okay. It's not crazy. If that all makes sense, it's good. I can go into how we can get it like realistic, so we can like use real mouse up and downs and like move up and down and left and right through it. I might as well do that. I won't probably do editing unless people want me to. That's okay. So we just got the CC flags. I don't really care about this stuff. That's all good. We got our content here. We can actually look at help. So if we just do this by normal, we can see one of the help commands. We can see, okay, if we go force type equals string, we can force it to be a string. Let's try that. What does that do? Huh, that did force it to be a string. Why? Well, because when we said force type equals string, right? It went back here and went, okay, force type is true. Okay, yes, we're in force type. Find me the second argument, which is what this magic is doing. You don't really have to understand what this is. It's just trying to find the second argument. Once it finds the second argument, if it equals string, it's going to set to this. So what that means is if we do something like force type equals cat, it would be like invalid argument cat. It's somewhat smart. Okay. And so if we want to be able to move up and down, the first thing we want to do is we kind of want to have like this like main loop here, right? So we're just going to implement a simple loop. I like doing them infinitely, but we probably won't do it infinitely here. I don't know. We'll see. We need some buffer because we're reading an input. Oh, maybe. We'll see. If we edit things, we're to read an input, but else we won't. And we're just going to read one character at a time. And we're going to use a special function called getch. Now, I've included a getch implementation in the source if you're on Windows. Otherwise, it probably won't work. I don't know why I put it for you here. Yeah, this is getch. You can mostly ignore this, but notice how it uses bit flags, right? Everything uses bit flags. And notice here how these are structs, not pointers. We don't malloc these because we don't need to. The lifetime of these are within this function. Okay, and all this is saying is don't echo. So when you press a character, we're not going to output it back to the terminal. So you won't see the characters get re-entered. If the input equals, oh, I see you aiming. The video will definitely be available to be downloadable. I don't know if I'll do too much more. We'll see. And then we want to do /033, which is going to be our escape key. So this is just some, you don't really have to understand how this works, but we're basically saying if we press escape, so for example, literally escape, right? Then it's going to input this key. So when you press left, up, mouse, and down, it actually sends a special signal to the computer, and the special signal looks something like this, followed by like A. So for example, in reality, you'll see it in your terminal as this. I press really this, right? So if I press, can I easily get it? I can't. It sucks. I'm trying to figure out a way I can get the actual keys to work. I don't think I can easily. You'll see it in a second. But basically, what we're doing is just going to send 3 characters one by one. So this is the first character, second character, third character. So we're seeing it. Okay, we can always ignore the second character since it's always going to be this. And then the third character, we can switch on. A, we know it's up. Right? Click inside. P, we know it's down. Yes. Side. Just have a habit of it. And this will be right. So we'll see in a second. And this should be okay, so there's going to be all our 3 characters, and we can have a default as well, but our default will just fall through and do nothing, right? So if we want to move up, we just want to kind of like move this current row up and down, or this current column up and down. So we can have something like, I'm just going to create a special class. I think I've got one here. I do not. That sucks. I'm just going to call CSV selected. Okay. Right? CSV selected underscore T. By CSV selected. You can create an int, row, a column. Maybe we have a flag. Right? So we create flags here, or we can just do Boolean saying like modifying. Say, are you modifying this value or not? Maybe if we're modifying it, we make it blink. And we can do all these kind of crazy cool new things. To include Boo, we'll need SDBoo. So how do we do this? Well, we're going to need to basically just check and modify his values. So if we want to move up, we're going to like say selected.row is plus plus or minus minus, I guess, right? Because we're moving up. If we're moving down, then the row will be plus plus. Like we're moving down the row. Move right, then we're going to move the column. Right? Plus plus, and the column left will be minus minus. Right? And if the row is less than 0, I guess, then we probably want to stop it. Right? But we don't actually have the length, so we can't really like stop it from going too far down. So we're just, I guess, going to we could like stop at a different level, right? Or just not show it, right? It shouldn't be too bad if we go too far. But we'll just stop it within the bounds that we can do it. You could add extra functions to see what the lengths of things are. If this is greater than, I guess it's going to start off being 1, isn't it? Yeah, it is. Okay. So this is going to make sense to have like column equals 1, row equals 1. So therefore, if column is greater than total number of columns, which we can actually find out, right? It will just be CSV as length, right? Then we can say selected column. Do the same thing for D here, right? We can just basically check this value down here. we are done. In terms of our movement. Now, that's all we really have to do. All we have to do after that is basically just print it out. So we can just do something like, oh, print out function here, like CSV, print CSV. We have to probably pass along this selected. So we'll modify the function so we can pass along selected. And we'll probably have to modify this. So we'll bring this down a bit. So it's selected, and we can go and we can modify the function, csv.h, and we can just add our selected. I'm passing this by reference because maybe I want the function to be able to edit it in the future. I mean, it doesn't really need to right now, but it doesn't really matter, right? I can still pass this by pointer. It doesn't mean I have to allocate it, right? It's still okay. And then down here, I'm just going to make this also the same thing. And I can use this function here, this function I mentioned before, this print record, right? This table apply. This is all it's going to do is call this function that we made before, that we added before, and call for every single record over the table. And because this is a function, we can't access things here. Completely inaccessible, right? There's no way for us to access anything here. There's no lambdas, none of that. So we have to like pass it in as a variable. Then we can grab it from here. Say, okay, CSV select, I think called. There's our selected data. Then we can say things like int color header, int color text header. Maybe just go like FG header, no worries, yeah, background header, FG row, background row. You can do all this kind of craziness. I don't know. I'm just gonna like make it white, flip these colors in the case of it being true. I'm just gonna say, hey, if selected row equals record row, then make it the other way around. Make it white. And then the same thing here. This background white. Oh, it's background black, right? So we're just going to switch these around. Okay, so that will set the bordering color, and then we can also set things here. You can make this like blink. Here's much flexibility. I don't really. You guys can do that if you want. Okay, and then this stuff doesn't really matter, but we should flip these colors, right? So we're basically just going to write the same colors, and we're just going to flip it in the opposite way. Back. And same thing here with BG. Right. Okay. Then we probably also want to do the same thing here, right? So it's that kind of repetition. But the thing is down here, we want to do for these headers. So some of these headers we want to set to a different color. We won't do that right now because we have to like add extra logic to it. Okay, so here's our CSV file. Not cat. I'm just going to load this one. Okay. And look, I can move up and down at least. I can't move left and right apparently. Oh, you know why? Because it's making the entire row that. See how it makes the entire all the columns this way? We want to do this for every single column. And this should be if the column equals. We can move the clear modifiers up. Do this, and then we can make. Oops. Oh, it should be just column. Okay, and then we can just run this. Again, no force type. Cat doesn't exist. And now we at least have some kind of moving up and down, but now we still have all the entire, like, it's got the row right, but now it seems to be like the entire row has to match, right? This is the problem. It's not just the row has to match, the column also has to match, right? So you can see how these statements are getting really complicated. So we probably could write them a bit nicer, but I don't really, time-wise, I just want this to be short. I want this to be almost, this is basically going to be it, right? So it's just kind of replicate that and make it not great, but it'll be good enough, right? Now we have the ability to select, and that looks all pretty good, right? So we can go up and down. I don't think this, as I said before, this can go all the way across. Don't necessarily stop that. But yeah, it looks pretty good, right? And so we could add columns here. By all we'd have to do would be doing this kind of set and deset. I guess we'd want to do it like here, and then we want to do like a clear modifiers, and then we want to do the text set and text clear modifiers down here as well. Right, and so we can just move this down all the way here, and set this bold as we're doing here, and we can just do the same logic that we did up here. But for row, right? So if the row is right, then we can set this. We just want to grab this row logic. And so I guess the easiest way of doing it, or the header logic, is we can just say if selected, column equals. And now we don't really have a header index here, don't we? But we can calculate our header index by grabbing where headers are, and then we can subtract it from CSV headers. And that will tell us our index, right? And then if so, we're going to use FG white, else we use FG black. We're going to use the same thing for BG white and BG black. Okay. We can stop this here and we can make, and we can see that now we have a scene that looks quite nice actually, right? We have ability to move around, and adding an editing button here is quite easy too, right? We could literally just have it so you press E and it allows you to edit a line, right? And so a simple way to do that would just be to go, okay, if the input equals this, sure do this, else if the input equals E, right? Then we can do printf this input, enter new value, right? And maybe we'll say this always has to be a string right now. We're not going to like pass it. We're not going to do like all this crazy passing logic, because all the passing logic that we had before, we could abstract into a function, right? But for now, we just do something like an fgets on it, right? And we can just go, okay, we have a buffer. It's up here. It's going to be 1024. It's going to be SDN. And then once it's done, we can just go, okay, whatever the value is at that index gets changed. So we can go see, it's called table index, maybe. Maybe I don't have table functions imported. I do not. We import our table functions, right, which gives us access to all of our beautiful abilities to index things. We can go, hey, grab me this index at this table. And the row is what we care about. And so the row is going to be our currently selected row. Right. And then give me this and grab me inside this. And you notice I don't really have to use it. I don't have to store anywhere. I can just use it. I'm just going to give me columns of sector.column. Right. Same thing that should actually be that. And for down, yeah, it goes like that. Grab me this, and then I'm going to edit the text and point the text to buff or string duper buff. I also want to add another value, so okay, it will be nice and do this, but I can just do something like this. This is a CSV record column. Okay. Right. Oh, it's actually let's do this, and we can do something like rec columns.text equals this, and finally rec of columns.type, and this will be it. Okay. And we can remake and we can recompile. And now we have the ability to press E, we can enter new value 10, and we have it 10 in here. Now it's breaking because it's including the new line. So let's make sure we strip that new line. Right. Okay, now it's stripped, we can remake and recheck. Right, and we have the ability now to edit these values, and we can go through one, right? Now, obviously, we don't have the flexibility to have these as numbers or digits, but that's really CSV. CSV doesn't say every column has to have the same value, right? So every column can be unique. And so if we wanted to do parsing, we would just have to basically do what we did before in CSV Reader. We could, probably make it a function, but really all we're doing is grabbing what this is, right? That's all we really need is this chunk here, and that determines what the type is. So we could have that as a function that would come out and give us a new object. Okay, so hopefully that was beneficial, at least for some of you. Hopefully that made some sense. I'll start recording now.